Welcome everyone back our lesson. Today we will introduce about the matrix array representation, and this is one of the lesson in the introduction to the quantum computing and the programming course. Okay, the last lesson we already learned about how we can represent the kernel one-to-one and linear operator. So today we will look how we represent the matrix, or it's called the matrix representation. Okay, so remember the last thing, we have a vector v and we have a basis, right? Yeah, and we have vector v, and vector v include about the n. We have this is we have okay, over here we have an n column, or we have an n elements. Yeah. So the matrix representation of linear operator we can define by this one. Okay, matrix is T, that means the linear operator. So this one we have a respect to B. This one is this one is a B. Okay, B. Yeah, B. Okay. Respect to the B, so we can you check. So if you have a and a vector v and a vector v1, v2, vn. So after we use the linear operator, so the matrix representation we can split to the n part. For example, this one we can linear operator for this one first. Yeah, this. And the other, yeah, this one, B, yeah, okay. The same for this part, we have the linear operator for this part. So after we transform or use a linear operator, we have this guy of yeah, this one is B. So we have a total about this is n multiply 1, okay, and represent after which use a linear. Have the other part is we can move to the linear combination. Just linear, yes, linear. So you can multiply h1 w. Yeah, so you can this one is multiply. Yeah, this one is you can multiply with this kind of weight, yeah, with weight. So yeah, and we have a B and D. Over here D, you need to actually over here D we need to definition. This is a D is about dimension, yeah, dimension. So over here we have a B and D. So actually D over here that mean yes, dimension. So you can represent back again. This one is matrix representation. Yeah, representation. And if we have n, yes, this one we have n or m, the value from the here element. So we can after we transform we can x1 1 n, right? So and after we transform to the two dimension, yeah, two dimension mn. So we can see a11, yeah. So you can amm. So this kind of two dimension the matrix. So you can see over here is dim is n, right? This is m. That is called column. This is kind of column. This is dim w. This is equal to the number of rows. Yeah, number of rows. So after we transform use a linear operator, and we have this guy of okay, this I have D. Sorry, this guy of actually it needs to make confuse dimension, the number of dimension or basis. Yeah, the previous maybe this one. Yeah, can be B or D. Yeah, D. This one is equal to D. Yeah, or B. This guy basis, yeah, basis, reflect basis, because suddenly is doesn't appear D over here, so make confused for you. So D over here is dimension, so it's a similar. So the matrix representation is kind of square the matrix. Square, you remember, is a square, that means over here M is equal to the N, okay? Square. Represent matrix representation T, so it's, remember this kind, it's kind of square the matrix, yeah. So, for example, you can see over here we have, we have vector V. This is a qubit. This is 2-bit. Okay, 2 bits. We have a 2-bit, and we have a W. So we have this kind of in the W the vector, and we have a basis about this 2 is 1 bit. 1 qubit, yeah, 1 qubit, yes, 1 qubit, this one is 2 qubit. So if we transform between the, the two part, we have from the C, right? C4, that means we transform from the 2-bit to the 1 bit. So we need to find about the, we need to find the matrix representation for the T. If the two the basis and the new vector D, yeah, the dimension. This is new, yeah, new. So after we transform your T operator, you can see T operator. So remember 0, this one 0. I think this one from the previous lesson. This one is 0. 0 vector. After we transform, you can use this one. I remember we have this 1 minus 1. Yeah. So this you multiply this one, so it's equal to this part. Yeah. Yes, that is equal to 1. Yeah. And but from this value you can transfer to the linear. This kind of linear transform. And linear transform, and to make sure it's match, we transform to the C, right? So if C, we transform, if the 1, 0, so we can transform to the, make sure this is 1 and this is 0. 0 multiple with any the value, we still the 0, right? So this kind of, the addition, the value doesn't matter. We only need to add over there to make sure yes, it's kind of linear form, yeah. Okay, after we multiply and we can see, okay, this kind of linear form, right? And let's go back over here. So if you see after we transform, it's a kind of format between the match C4 and C2. Yeah, and after we transform to the new dimension, so it's equal to this kind of value. So yeah, so it's equal to this kind of value. And you do similar for the qubit 1, qubit 1 and qubit 2, qubit 3. Yeah, qubit 1 or qubit 2 and qubit 3 is similar. And this kind of value you get after. And after you got, you got that kind of transformation. So you move back this kind of formula, the vector, and you can combine and see this kind of linear operator and the matrix. This kind of matrix operate of the matrix representation for the linear operator is equal to this one, and this guy is the final result. Okay, final result combined with this guy of combine this one, and this one. So you can see, yeah. You see this one is equal to this, right? This one, right? Yeah. Okay. So that is how we represent or we define the matrix representation in to support transformation between the linear operator between the two vectors. Yeah. So what about we have the other new concept is called the function computing and matrix computing. Okay, computing just means you multiply or you add or you subtract. Okay, so over here we have a two vector. Yeah, we have two vector V and this guy basis. Okay, B is just basis, and we have a vector W, and vector W we have a D is kind of basis, and vector B is kind of basis. Yeah, this slide is much better. I think. Okay, over here is I think we have after we transform and we use a linear we transform between the V and W, we transform, right? So we have a kind of matrix representation. So this kind of B and D, the relationship between the two one based on the linear operator, so it's equal to this part. Yeah. And that is for matrix matrix computation. Yeah. What about the we have the function? The function. So we have this guy. We have a new the transform from vector Vj. So that can be the new this kind of function. Yeah, the function. So this kind of function, after you apply about the linear operator and this linear combination, you have a same. And but over here, after you have transform, you have this is function for linear operator and equal to the matrix representation multiply with the variable x. Yeah, variable x. This is function. And this kind of matrix, okay, a little bit opposite in this title, yeah. Okay, this is how it's proved. So you can look more detail how it's proved in slide. So step by step. So actually take care more about this part because we how we linear this how to linear, yeah. Okay. And this is a kind of example how you do in the find the format in linear operator, actually linear mapping. So check actually the key point. Yeah, if you see after we have from the quantum state, you can move to the how you can plot. How you can plot the quantum state in the the angle sin cos. So you can check. Yeah, you can see how the angle in the vector. Yeah, so that is how you transform. So this yes, the solution for the previous one. So you can check more in detail. So okay, the summary of this part we have the matrix representation, and we have a T. So this one we have a T equal to, for example, x A1G. Yeah, so how we calculate about the matrix representation for the linear operator and the function computing and the matrix computing. Okay. So see you the next lesson. We will look more about how we can check the new concept. Okay.